So, in the earlier lecture, I talk about a brief introduction to WKB approximation. Today, I am going to talk about the mathematical formulation of WKB approximation. So, for this, consider Schrödinger wave equation. Schrödinger wave equation, and the equation is like this: minus h cross square by 2m d square psi over dx square plus v, and v is not a constant but it's a function of x. Psi is equal to e psi. Its situation is like this: say it is the energy of the particle and it is the potential is a function of x, and it is changing slowly, it is varying, and this is the classical region in which I am going to talk about. Right, I will talk about it in only this, the classical solution of this equation. So if we try to look at this, then the energy of the particle is greater than equal to Vx, and Vx is not a constant, it is a variable. We have to keep this in mind. This is the main point of the WKB approximation, and let me do little more algebra. So here I can write down it as d square psi over dx square. It is E minus Vx psi, and it is 2m over h cross square with negative sign. It can be written like this, and it is d square psi over dx square is equal to 2m E minus V and V is a function of x over h cross its under root and whole square. Means this term can be written like this. Now this is the value of k. This is the value of k. So I can write down it as d square psi over dx square, and negative sign is also there, so it is minus k square psi, and it's equal, right? So this is our equation. And let me recall one more thing. As we know that P is equal to h cross k, so that means this k can be written as P over h cross. So if I try to write down this equation, then d square psi over dx square, it can be written as minus p square over h cross square psi. Here p is also a function of x because p is also a function of x, so px can be written as 2m E minus Vx. It can be written like this, right? So this is basically the momentum of the particle, but it's not constant, it keep on changing. So it is the momentum of the particle with total energy E and potential energy Vx, right? That's what we have to keep in mind. So now for the classical region, as I discussed here and in the earlier lecture also, so for the classical region, as discussed in the earlier lecture, means E is greater than Vx. So after solving, let me call it as equation 1. So after solving equation 1, psi should be like sinusoidal. Psi should be like sinusoidal, but its amplitude must change with x, that is a is basically a function of x. So keeping this thing in mind, and also as discussed in the earlier lecture, that let me try to write down the wave function like this, that psi is equal to a, which is a function of x, and exponential of iota phi x. This is a new thing which we have to keep in mind. So this is the wave function which I am choosing. Now my purpose is to find out a, x and phi x. This is our objective, right? So to do this, let us do one thing. Let us take the derivative of psi. So now what I did, I have chosen that psi should be equal to ax exponential of iota phi x, which we have to keep in mind. So to determine a and phi x, let us try to find out d psi over dx. Means I am interested to find out the derivative of it. So it is a is a function of x and exponential of iota phi x, right? So if I take its derivative, how things looks like. So derivative of first function and second function will be like this, as it is, plus first function as it is and derivative of second function. So it can be written as a prime represents the derivative with respect to x. So a prime exponential of iota phi x plus ax, or simply a, and again iota exponential of iota phi x, and again derivative of phi x, and iota can be taken outside. So I can write down it as a prime plus a iota, or iota a phi prime, because it is the phi prime, and this is common for the both, so it can be taken outside, right? Now let us take its second order derivative. Now d square psi over dx square, it can be written as ddx of d psi over dx, and the value of d psi over dx is this one. So I can write down it as ddx of a prime plus iota a phi prime exponential of iota of phi x. We have to take its derivative now, right? So what should I do? Let me take its derivative. So it is a first function and it's a second function. So first of all, I will take the derivative of first function, and second will remain as it is, plus first will remain as it is, and derivative of exponential of iota of phi x, right? So how it can be written as, it is a prime derivative of first as it is, so a double prime plus iota ddx of a phi prime and exponential of iota phi plus it is a prime plus iota a phi, and its derivative is iota exponential of iota phi and derivative of phi, right? So what it will be, it is a double prime plus iota, it is a prime phi prime plus a phi double prime. Here I have applied the product rule, and exponential of iota phi will remain as it is, plus iota a prime plus iota a phi, sorry, prime is also there, yeah, and it is exponential of iota phi, and here I have write down it as phi prime, right? So it is equal to a double prime plus iota a prime phi prime plus plus iota a phi double prime plus iota a prime plus iota square a phi prime, and this is multiplied here, so it is phi prime and phi prime, and outside I can take exponential of iota phi. So that's what I am getting here. Now it is equal to what? Let's say equal to a double prime. Let us put these two terms together, plus 2 iota a prime phi prime plus iota a phi double prime, and here it is a, so iota square is, so it is minus a phi prime square, and it is exponential of iota phi. So let us substitute these values in equation number 1. So if I put these values in equation number 1, let me recall that what is equation number 1. So equation number 1 is like this. This is d square psi over dx square is equal to minus p square over h cross square. Yeah, it is p square over minus, right? So let us put their values. So its value will be a double prime plus 2 iota a phi prime plus iota a phi double prime minus a phi prime whole square. Exponential of iota phi is equal to minus p square over h cross square. It is a exponential of iota phi. So this will cancel out with it. So we are having only a double prime plus 2 iota a prime phi prime plus iota a phi double prime minus a phi prime whole square, a phi prime square, and it is equal to minus p square over h cross square into a. This is what I am getting, right? So let me rearrange it now. So let us rearrange real and imaginary parts. So it is a double prime minus a phi prime square, right, plus iota 2a prime phi prime plus a phi double prime. It's equal to minus p square h cross square, and a is also there. Sorry, I missed in the, yeah, a is also there. Let me go back. Yeah, a plus iota 0. So this is real and this is imaginary part. So this is equated with the 0 and this part is equated with this part. So what I am getting, this is a double prime minus a phi prime square is equal to minus p square over h cross square a, and it is 2a prime phi prime plus a phi double prime is equal to 0. And this part can also be written as, this is if I take a square phi prime and take its prime, means its derivative, it's equal to 0, so then this term is equal to this one. So if I integrate it, then it is a square phi prime we are getting, and it is equal to some constant, and let us call it as c square. So c square is a integration constant, and square we have taken for the sake of simplicity, right? So that means from here I can calculate that a square is equal to a is equal to c over phi prime under the root. That's what we are getting here, right? So this is the value of a, and let us now try to look at this part. From here I can write down a double prime is equal to a phi prime square minus p square over h cross square into a, and a can be taken outside, so I can write down phi prime square minus p square over h cross square, and a is outside. And here, since a varies very slowly, so a double prime can be ignored. So if I ignore it, then I can write down that 0 is equal to, or I can say that a phi prime square minus p square over h cross square is equal to 0. What does it mean? That means phi prime square is equal to p square over h cross square. So phi prime I can write down from here is equal to p square over h cross square, or simply I can write down that d phi over dx is equal to plus minus p over h cross, if I taking square root on both sides, and if I integrate it, then on integration what we are getting phi is equal to plus minus 1 over h cross and integral of px. So this is the value of phi x we are getting, and this is the value of phi prime, right? So phi prime is basically this one. So that means the wave function can be written as, so the wave function, the psi is equal to a exponential of iota phi x, and a is also function of x. So in place of a I can write down c over phi prime under the root exponential of plus minus iota over h cross, it is integral of px dx. So this is a way that how this can be written like this. Since this phi prime is proportional to p x, so keeping this in mind, I can write down simply it as this wave function psi is nearly equal to c over p, and p is a function of x. and exponential plus minus iota over h cross integral of dx dx. So this is the value of the wave function while we are using WKB approximation, right? So this is all about WKB approximation and its mathematical formulation, and this is all for today. And in the next lecture I will discuss some quantum mechanical problem using WKB approximation.